So let's continue our discussion of energy conservation. We want to show mechanical energy conservation in a few special cases. Now, mechanical energy is sum of kinetic energy plus potential energy. Okay, let's say free fall. You have a ball initially here and it dropped to here. What is the total of mechanical energy for this ball? So basically, you need to find out initial kinetic energy, initial potential energy, final kinetic energy, final potential energy. Okay, we're going to use my favorite kinetic energy equation again. So apparently, whatever the initial velocity, so its initial kinetic energy is 1/2 mvi squared. Its initial potential is mgyi. This is initial mechanical energy. Now, what is final mechanical energy? 1/2 mvf squared plus mgyf squared. Now, vf squared equals this, so I just replace vf squared with whatever in this bracket. And you combine all the terms, you find it's actually equal. So you see the mechanical energy of the ball here equals to the mechanical energy of the ball here. Now it also holds if you have something sliding down an incline. You just need to do the same thing, the kinetic energy, the kinetic equation. And in this case, if you know on the incline, if we ignore all the friction, you have the acceleration of the object is g sin theta. However, you see the displacement, so there's a displacement, this is a change in h. There's a theta, so displacement times sin theta equal h. So displacement equal h over sin theta. That's why I have this, that S equals change of height over sin theta. And this sin theta cancels. You have the same thing. And you find out the kinetic energy of the object here increased by the mechanical energy, which is kinetic energy plus potential energy, equals exactly what you have here. Kinetic energy here, potential energy here. So which means mechanical energy is conserved here too. What's going on here? You have a small child slides down 4 different fractional slides, A, B, C, D. And they have the same height. Now just using your intuition, which slide the child would have the highest speed at the bottom? Now pause this video for maybe 30 seconds to 1 minute to think about it. Which one is your answer? Okay, I think you figured it out. The answer is D. And what's the reason? Is that for this one, mechanical energy is conserved. Mechanical energy here and mechanical energy here is the same. Mechanical energy here, 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 they're all the same. So you have at the bottom 1/2 mvf squared, they all equals to mgh. So they should all have the same velocity. And why mechanical energy is conserved? Let's discuss. Why we have mechanical energy conservation. So we have the condition for mechanical energy conservation. If the system is isolated and the force that are doing work is only conservative force, if only conservative force is doing work. So we can prove it. Now we have the work energy theorem. If you can recall, the total work done by a force equals the change of kinetic energy. Now we want to split the work because we have two different kind of forces, right? The work done by other forces. We want to split into the work done by other conservative force and the work done by non-conservative force. And then you have the work done by the conservative force equals negative of change in potential energy. That's the definition of potential energy. Change of potential energy equals negative for work done by conservative force. So you have this blue line connecting the dots here. Okay, you have this is work energy theorem. This is definition of potential energy. So you have the work done by non-conservative force equals change of kinetic energy plus change of potential energy. You can also write it as change of mechanical energy. So what's happening if there's no non-conservative force doing work here? So you will have change of mechanical energy is zero. What does change of mechanical is zero mean? Okay, if W and Z is zero, you would easily have mechanical energy conserved. Mechanical energy conserved, which means that if this is zero, you have initial mechanical energy equals final mechanical energy. So that's really the takeaway message here. If the net work done on an object by non-conservative force is zero. So in other words, the only force doing work are conservative force. Then you have mechanical energy conservation. You have KEF plus PEF equals KEI plus PEI. Now if this looks complicated, you just say, let's say we only have one conservative force, one potential energy, gravitational potential. Then you easily build one equation. 1/2 mvf squared plus mghf equals 1/2 mvi squared plus mghi. Very simple equation. That is mechanical energy conservation. Okay, what's happening if there is non-conservative force doing work? Now, if you have non-conservative force doing work, then the work done by the non-conservative force is change of mechanical energy. Okay. Very simple, so you have to understand this. So this slide summarizes everything we want to talk about in this chapter. So you have to try to understand if there is only conservative force doing work to the system, the mechanical energy is conserved. So you have a very simple equation. 1/2 mvf squared plus mghf equals 1/2 mvi squared plus mghi. Initial mechanical energy, final mechanical energy. So I have several examples in the example video, the conservation of energy example video. Please watch them if you're confused. And this is the case if there is non-conservative force doing work, for example, friction. Okay, then the change of mechanical energy equals to the work done by friction. For example, if you slide a book across the table, Now, initially the book has kinetic energy. Eventually it stopped. Why? Because the work done by friction equals change of the mechanical energy, which in this case there is no potential energy, so you have mechanical energy equals to its kinetic energy. Mechanical energy decreased, and the decrease of mechanical energy equals to the work done by friction. Now, where did the energy go? It becomes thermal energy. So the book have friction force between the book and the table, and this friction doing work becomes thermal energy because the energy of the book would slightly increase. Now this is the most general form of energy conservation, and it's always held. Energy conservation always held no matter what's the circumference. We always have energy conservation. Mechanic energy plus the total work done would equal to final mechanic energy plus the change of internal energy, which is actually thermal energy. Okay, let's just do one more example. So you have a hawk jumping down a tall building 100 meters high. When he reaches the ground, he has velocity 40 meters. How much work would have been done by gravity in vacuum? So if hawk jumped from a 100-meter tall building, what would be the work done by gravity? Very simple, mgh. Okay, you can plug in all the numbers yourself. What's the real change in kinetic energy? Simple, 1/2 mvf squared, 1/2 vi squared, and vi is 0. So it's actually just 1/2 mvf squared because vi is 0. How much work is done by friction? Ff is change of mechanic energy, which is Kef plus Pef subtract Kei plus Pei. Okay, Pef, you can choose it to be 0. And Kei, which is also 0. So you have this one 0. Pf 0. So you have is Kef subtract Pei. And the Pei is mgh, right? So it's 1/2 mvf squared subtract Pi, which is mgh. And you'll figure out it'll be negative number, which makes sense because friction, kinetic friction always doing negative work because kinetic friction is always in the opposite direction of the motion. Okay, that's it for chapter 8, energy conservation.